Today we are explaining Harness Handbook, making evolving agent harnesses readable, navigable, and editable.
What problem does this paper address in evolving AI agents?
An agent harness builds prompts, manages state, calls tools, and coordinates execution. When that harness must change, a request describes behavior, but the repository is organized around files and modules. The developer still has to recover every implementation site that realizes the behavior. That mapping is especially difficult in production harnesses because one behavior can cross knowledge staff and files, execution stages, and state. Code search can find related words, but it does not reconstruct the runtime behavior or guarantee that every relevant site was found.
So what representation does the paper add to make that mapping explicit?
The authors introduced the Harness Handbook, a behavior-centered representation that links runtime descriptions back to source code. It has a 3-level document tree, a system overview, component overviews for execution stages, and source-backed unit details. A complementary state register records relationships that cross stage boundaries.
How does a reader move from a broad behavior to an exact source location?
The reader starts at the system level to identify relevant stages, moves to a stage overview for inputs, outputs, dependencies, and local state, and then follows the linked unit entries to source files, functions, or regions. The state register adds stages that are coupled through shared state, even when their files are far apart. The handbook is constructed from the repository in 3 phases. Static analysis first extracts source-grounded facts and a program graph. Behavioral organization maps those facts to execution stages. Hierarchical synthesis then produces the learn to L3 tree.
Where does the proposed navigation policy enter the modification workflow?
The policy is called Behavior Guided Progressive Disclosure, or BGPD. It narrows the search from course to find first relevant stages, then state-coupled stages, then the most relevant or stacked entries. The planner proposes locations from the handbook and verifies each candidate against the current repository. The workflow also resynchronizes the handbook after every non-empty code diff. It reparses changed source, matches added, removed, and modified units, and refreshes only the affected structure when the stage skeleton remains valid. This keeps the behavior map tied to the evolving repository instead of treating it as a what-I'm index.
How did the authors test whether this organization actually improves planning?
They compare a baseline planner that explores the repository directly with a handbook-assisted planner that follows BGPD. The model, requests, repositories, tools, and decoding settings are held constant. Only handbook access and navigation differ. 2 open-source harnesses contribute 30 behavior-driven requests each. 3 independent judges score localization, scope control, and reasoning. The combined score weights localization at 1/2, with scope control and reasoning at 1/4 each. So identifying the right code sites is the central part of plan quality.
What does that score measure, and why give localization the largest weight?
The equation defines the overall plan score S. S subblock measures whether the proposed edit sites are accurate. S subscope measures whether the plan avoids unnecessary expansion. And S subreason measures the quality of its rationale and evidence. The weighting reflects the paper's focus. A well-reasoned plan is still unusable if it points to the wrong implementation sites. The first result is higher plan quality without a larger token budget. On Codex, the handbook-assisted win rate is 38.3% versus 28.3% for the baseline. On Terminus 2, it is 45.6% versus 26.7%.
Is the gain only coming from one judge or from spending more tokens?
No, the improvement remains positive for all 3 judges. At the same time, average planner use falls from 0.10 million to 0.089 million tokens per Codex request, and from 0.058 million to 0.053 million on Terminus 2. The handbook improves the search path rather than buying quality with extra context. The dimension breakdown explains where the improvement comes from. On Terminus 2, the handbook gains 12.2 points in localization, 6.7 in scope control, and 4.5 in reasoning. On Codex, the corresponding gains are 2.2, 1.1, and 3.3 points.
Does the handbook help only with the easiest kind of localization?
The evidence says no. Across query, cross-file, and search hostile requests, every harness by type comparison favors handbook assistance. The gains range from 16.3 to 33 points. Codex improves most on query requests, while Terminus 2 improves most on search hostile requests. The localization test gives a second line of evidence against independent reference plans from Opus 4.8 and GPT 5.5. O20 for recall, precision, and phone comparisons are higher with handbook assistance. Phone gains range from 5.0 to 18.8 points, while complete localization failures fall by as much as 25.9 points.
What should we carry forward from these experiments?
The central contribution is a behavior map that stays connected to source code while an agent navigates from system behavior to implementation details. BGPD makes that navigation progressive and verifiable, and resin explanation keeps the map current after edits. In these tests, that combination produced better plans, fewer planning tokens, and more accurate site localization across types. That wraps up our explanation of Harness Handbook, Readable Behavior Structure, Navigable Source Links, and evidence that the representation helps agents plan changes in evolving harnesses.